So third goal for the day was, or this lesson, is got something to do with these composite functions and being able to play around with them, and then ultimately to figure out whether or not they're even and odd and some special properties that they might happen to have. So we've got two functions here. We've got our f of x and we got our g of x, and we're going to start off with this one. Find the f of the quantity x plus h. Well, what does that mean? F of the quantity x plus h. That means that everywhere I see a variable in the f function, I'm going to replace its variable with the quantity x plus h. And the thing that gets a little confusing for people is, well, I'm replacing an x with a different kind of x. Yes, you are. So we're taking this function that originally was something squared plus 2 times something plus 1, and everywhere we see that something, we're going to replace it with an x plus an h. And now it's a matter of just going through and multiplying out this binomial. So I think this is x squared plus 2xh plus h squared plus 2x plus 2h plus 1. And if we check, I don't think there's any like terms there. That problem is more just an exercise in reviewing algebra and functions. Second one, or B and C, these are what we call composite functions. Okay, composite functions, meaning fog. If it says fog, what we're really talking about is f of the function g of x. So what we're really doing then is we're now treating g of x as the variable that's going to get placed into the f function. So something similar to what we just did a second ago. So if we take the f function and we write it out with the variables blank, we got something squared plus 2 times something plus 1, which is very, very similar to what we just did above in red. But now everywhere I see that, I'm going to put in the g of x function. Well, what's the g of x function? It's x minus 1. So everywhere we see a variable in the f function, we're replacing that variable with the g function itself. So now if we take this and we actually go through and multiply it out, x squared minus 2x plus 1 plus 2x minus 2 plus 1. Clean all that up. What's that spell? Well, those two x's are going to drop. Plus 1 minus 2 plus 1. After all is said and done, that composite function is just x squared. And when I look at GOF, so to speak, or your f of, or g of f of x, now we're going to reverse this process. Now we're going to say that g of, and I'm going to reverse the colors here so you can kind of see what happens, g of now f of x. The second one always goes inside the first one. So if we take the g function and we rewrite it, well, our g function has a variable minus 1. Well, what is that variable? That variable is now where we're going to put the f of x function, which is x squared plus 2x plus 1. Forgive the squeeze there. Take that, put it together, clean it all up. What are we going to end up with? This time we're going to end up with an x squared plus a 2x. So those are composite functions, a little bit of a review. We'll need those when we start talking about inverses and things. Now, even in odd functions. Even in odd functions is actually a shortcut. And what this is supposed to do eventually, as we start to do things with area under curves and things like that, this is going to provide a huge shortcut for us. And the shortcut is when we notice this is going to cut either all of our work completely out or it's going to cut half of our work completely out because of the properties of these graphs. So an even function, to make things as clear as possible, has symmetry about the y-axis. Symmetry about the y-axis. If I wanted to make you a real quick graph of an even function, the simplest equation I can think of would be a y equals x squared. Because what's on the left side of the y-axis exactly matches or mirrors what's on the right side of the y-axis. Those are even functions. An odd function has symmetry about the origin. Symmetry about the origin. So that means whatever effectively, the best example I can give you is y equals x cubed. So y equals x cubed, we talked about a speed curve, or we talked about the tangent graph. That one's an odd function. That basically means whatever's in quadrant number 3 mirrors kind of mirrors whatever's in quadrant number 1, and whatever's in quadrant number 2 kind of mirrors whatever's in quadrant number 4. To test even and odd, it's actually kind of cool. It's the same test no matter what. If I do f of the opposite of x, that's all I have to do. I plug the opposite of x in and I look at the result. If it turns out that I get my original function back, then I'm talking about an even. My function is even. If it turns out that I get the opposite of my original function back, then I'm talking about it being odd. If it turns out any other way, that means it's neither one. And what you're going to find is most graphs are neither one. So let's test this out. So even, odd, or neither. Now, if you can make a graph, use that to save yourself some time. If you're not sure what the graph would look like, then you go through the test, f of the opposite of x. So if I do f of the opposite of x, that means everywhere in my function that I see a variable, I'm going to replace that variable with the opposite of x. So here we had two variables. We replaced them both with the opposite of x. And if we clean that up, a negative number cubed is still negative. And now I'm adding. Well, how does that result compare with my original function? Well, you know what is interesting? Looks like if I factor a negative out of both of those, I would have exactly the opposite of what I started with. And if that's the case, this is an odd function. F of x equals x squared plus 1 if I do the same thing. Now, let's do the test first, and then we'll prove it to you without the test, or maybe you've already got this figured out. If I do f of the opposite of x here, I'm going to do the opposite of x and square it, and I'm going to add 1. So if I do the opposite of x, the opposite, and a negative number being squared would be positive. What does that compare? That is exactly the same function I started with. If that's the case, this function is even. And I got to tell you, if it were me, I would not have wasted time with this test, because I know that x squared plus 1 is a parabola that has a vertex 1 unit above the origin, and it would definitely have symmetry. So I could look at this and say that this graph is an even function also, based on what I've learned in pre-calc or in previous classes about my graphing. An example, what happens if it's neither one? So let's just put a real quick C down here, and let's say I called this function f of x is equal to x squared minus an x. So let's say that I did that. If I now did my test, f of the opposite of x squared minus the opposite of x, clean that up. Here's an x squared plus an x. How does that compare with what you started with? Well, you'll notice the signs are kind of goofed up. You're comparing these two things. How do they compare? Are they exact opposites of each other in sign? No, because one term matches and one term doesn't match. Are they exactly the same as the original function? No, this graph would be neither. And by the way, most graphs are going to turn out to be neither even nor odd.